for coming to our second part again of this academic year. Today, we're very honored to have Professor Scarani talk to us on randomness. So, without further ado, Professor Scarani.
So I will do something very introductory on the Prof. CQT. I thought randomness is an interesting topic. And I would like, if possible, you to have as an open-minded attitude in the sense that what I'm saying here, I mean, don't take these as the deep wisdom of someone that you can't understand, you really admire. You know, these super cheap topics I have to learn by heart what this guy is saying, no? Because anyway, I cannot possibly understand. I will try to bring up the topic of randomness is a topic that, of course, there will be a few things that you couldn't anticipate, but try to guess what I'm going to say. That will be the way, or try to follow at some point it will be a more mathematical proof. Try to follow it, because I think most of it should be concerned. Of course, I'm here to sort of guide you, because I'm going to synthesize in this talk lots of thoughts and discussions and works that have been going on. Okay, so of course, in a sense, there is some work of synthesis. So, what do you mean by random? Unpredictable. Any other? No other option. Well, turns out it's the right question. It's the right answer, sorry. So it's indeed it took quite some time even to phrase this, at least in mathematical terms, right? Because this has a small problem. If you are too much into a philosophical notion of randomness, this has a small problem that I'm going to bring up for you now. And essentially the problem is unpredictable for whom? Because in the act of prediction, you have to say, okay, who is the predictor? Who? A human being, the collection of human beings, God, the universe? Which information do you give me in order to predict this thing? Right? It's not any observer. So that's the problem of randomness for whom. So let's go a little bit back now. And I want to mention that unpredictability normally is related to insecurity, right? Because if I cannot predict something, maybe something bad is going to happen to me. We have many examples. Here I took these examples. One is the famous subprime crisis, 2009. So it's like economic crisis where, once it happened, everybody was saying, oh, it was obvious going to happen because all these speculations and so on. But not only the stupid mayor of the Norwegian lost money, but also real experts that were working in the stock market and in financial lost a lot of money. So you say, why did guys, if it was so obviously predictable, why they didn't predict it? Okay, earthquakes are notoriously bad for prediction. I said this one not because it's the most recent one in Italy in that part, as you know, there has been something more recently than that, but because the Italian magistrates managed to convict 7 scientists for not having predicted that event, which is probably the mafioso people who built the houses without the good specifications are not in prison, but the scientists went. So somehow, this is one of the problems of randomness. It's difficult to accept that someone is unpredictable for everyone. Right? You would say, well, there must be some experts out there that knew the answer. Of course, this tries for kind of conspiracy theories and what may not be as well known, but once I say it will become obvious as well, is that unpredictability is related to security, not only to insecurity. So there is something that we believe is unpredictable for everyone. And this is my password. Right? Because if I would think that my passwords are predictable by someone, I would not use that password. And this password gives me security. So in essence, cryptography can be summarized like that. Random for me is bad, and random for the others is good. Okay? If it's random for the others, it gives me security. If it's random for me, I'm in trouble. Or I may be in trouble. And that's the essence of cryptography. Cryptography means the arts of exchanging secrecy, of keeping secrecy. Okay, so that was just a sort of introduction. I think with this I do the general introduction on the topic of randomness, just to show that there are these concerns. And of course you may say precisely, oh yeah, but this is a very operational definition of randomness, and that's what we use in physics. It's something that, okay, unpredictability. So there must be someone that, or something, some pieces of information, and given those pieces of information, I can or cannot predict what's going to happen or what has happened. Now, very, very, very short history. I like history because I think we should put things into context, and when we look into history, things are much more complex than what they actually are. As you know, in physics, we are sort of accustomed to thinking in terms of determinism. Okay, so everything is determined from, and of course, this is a long history. We can go back to the Greeks and whatever. But okay, since it's a very brief history, I wanted to read the famous extract by Laplace. That of course wrote it in French, but I found an English translation. So in the book, in the Théorie analytique de probabilité, which means analytical theory of probabilities, which is, by the way, one of the first systematic treatises in statistics, 1812, not so long ago. So Laplace wrote, we may regard the present state of the universe as the effect of its past and the cause of its future, an intellect which at a certain moment would know all forces that set nature in motion and all positions of all items of which nature is composed. If this intellect were also vast enough to submit this data to analysis, it would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atom. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes. That's a famous statement of physical determinism, also called the Laplace demon or Laplace intellect. Now, what happened in the 20th century, you may know this, that in the 20th century these key positions were challenged. So on the one hand, the second statement, they are vast enough to submit all these data to analysis. People say, yeah, it's a bit tough, no? We'll have a big one day with computing machines, 1812. More is also the time where Babbage started with calculating machine. Pascal, of course, had some mechanical calculators much earlier, but they were just doing calculations. Now we know this is impossible in practice, right? Because we will always have finite computational finite computational resources, and yeah, so therefore my computer or yours, this one is much more powerful than any supercomputer I had when I was an undergraduate. But even with the rate of progress of computing nowadays, well, no way that we can, and there are some tasks that are known that go very, very badly with, so in practice, this intellect must be sort of superhuman. And this gives rise to things like deterministic chaos. Of course, this is true for complex systems like the weather. That's, as you certainly know, that's the reason why the weather is hard to predict. Because to model the weather, it requires a lot of data, and at some point you do some coarse graining, and this coarse graining may lead you in trouble. But also, in the 1970s, people noticed that simple systems can also, 2 or 3 degrees of freedom, can also exhibit this kind of complex dynamics, unpredictable dynamics, and this is a topic that you may find one day in advanced mechanics, maybe it's called that module or some level 5000 thing. Well, but the problem is the other one. So, quantum physics comes with an even more striking statement that it will be impossible in principle for someone to know all forces and all positions, okay, we would say all positions, not momenta, of all the particles. So that's a pretty striking statement. And that's the one I'm going to focus on. I just want, before going into that one, to sort of do a map of where we are now in the discussion to avoid confusion. So we said the random is unpredictable. You can have unpredictable behavior involving humans, you know it pretty well, right? Of course, collective, stock market behavior, polls and crowds and so on can behave in an unpredictable way. Individual, like criminal behavior, and if it would be easy to predict who is a criminal, it would be easy to prevent crimes. And then we have, okay, within that box comes the famous topic of free will that I will not discuss in this talk, because we are taking the other arrow, the arrow that randomness that does not involve humans. And as I mentioned, there are this computational randomness. So randomness that is not unpredictable in principle, but it's just that you will never have a computer powerful enough to compute those things. and the claim of quantum that this would be sort of what we call intrinsic randomness, namely that even with an arbitrary powerful computer, it's simply impossible to predict some things. Okay, so from now on, so this being the map of, if you buy a book on randomness, there are a few good books, I can tell you the titles later, if I remember them, otherwise they're in my office. They will speak of all these things. Also because there are plenty of nice anecdotes to say, polls that were screwed up, you know, things that happened, statistics that were misinterpreted, very funny things, but I will focus now on the quantum part. And again, history. Don't worry, the mathematics will come. It's in only 9 minutes and 14 seconds, so thanks to... So how does this claim of randomness come in quantum theory? Do you know what is the foundational date of quantum mechanics as we know it now? That's a very important date in... So in 1900, Planck comes out with his black body radiation, and 1905, Einstein photoelectric effects, and so on, mess, 1911, Bohr, discussion. There's 1 year when two guys independently invent quantum mechanics, and a third group of guys finds out that in fact they invented the same thing, although they look very different, the mathematics. And it's here in 1926. In 1926, Heisenberg and Schrödinger independently invent what we now call quantum mechanics, and it's exactly the same quantum mechanics that I was teaching this morning, Vito Pereira is teaching to some of you. That one is invented in 1926. And in the same year, Max Born, among other things, he proposes that the way to interpret this formalism, mathematical formalism, is to a probabilistic interpretation. Now, what happens with that? Einstein writes to him immediately, saying this cannot be, right? So quantum mechanics calls for a great deal of respect, but some inner voice tells me that this is not the right track. The theory offers a lot, but it hardly brings us closer to the old one's secret, an expression for God or whatever Einstein had in mind for that. For my part, at least, I'm convinced that he doesn't throw dice. Okay. But people like that. So forget about Einstein. Everybody, Bohr and others, endorsed immediately this interpretation. It becomes orthodox. In 1927, something other happens, that Heisenberg comes up with his famous uncertainty relations, and which are correct, and he tries to explain them and he gets it wrong. So if someone teaches the Heisenberg microscope or the photon microscope or the gamma ray microscope and so on, it's wrong. I mean, there is an element of wrongness there. So it doesn't explain the randomness of quantum physics correctly. That's what happens when you try to do outreach. Okay, so fortunately today I think I don't say many things wrong, but that sometimes you know, you're pressed to say, can you explain please quickly what is the meaning of your results? And yeah, sure. And no, it's not that. 1932, von Neumann is okay, technical result, you don't care. 1935, Einstein, that is still not happy with the thing, with two colleagues come up with an argument that allegedly proves that quantum mechanics cannot be the ultimate thing, as he said here. So you see also how these persons were thinking and thinking and thinking, not giving up, say, okay, fine, the whole community has accepted that, I also accept it, right? And also Schrödinger comes up with this metaphor of the cat that you might have heard, and that the cat is alive and dead at the same time. You know, in an outreach talk, someone asked me if it works also with dogs. Yeah, sort of. Also, okay, and then in 1964, there are some things happening in between, but essentially, okay, one thing that happens in between is that the physics evolves into what is technically called the shut up and calculate phase. It's a technical term. So if you say shut up and calculate, people know what it means. You know, maybe you can't imagine what happened at that point. So with what these guys have done in 1926, it became possible immediately to explain physical phenomena that were completely impossible to understand before. Solid state physics. Why some materials are conductors, some other are insulators. Magnetism. There's no magnetism in class. There is an impossibility proof of magnetism in classical physics by Van Vleck. But you have to explain why magnetism is there, right? Paramagnetism. Many dozen people hanging around there that probably are late for the and definitely are late. So And then, of course, all the particle physics, all the nuclear physics. One of the things that triggered quantum mechanics is radioactivity. Where does this come from? Both the nuclear. So all these things become possible to explore. And and there's some people that, well, I don't like this theory because I don't understand. Forget about it. We have so many things to do, to compute, to predict, and that's the period of shut up and calculate, which is fine. In the middle of this period, because it's not finished in 1964, a guy called John Bell, who was a particle physicist doing particle stuff and so on, in his spare time, derived something that I'm going to show you now. In between, there are some interpretation of things. I gave some part of this talk to other people that are more maybe advanced in their knowledge of quantum mechanics. So now the quantum claim, as I said, is very strong. So on the one hand, we can have the objection of the philosophers, that is something like, how can you possibly, I mean, you are just a physicist, right? How can you possibly come up with something that say you are intrinsically unpredictable? How do you prove such a claim? Right? Or is it a matter of faith? Is it a matter of pull? Like most physicists believe that there is something intrinsically unpredictable, and it's sort of, if you want to be accepted by the community, you better tell this, because otherwise I don't hire you. Okay? Is this what's happening? Now, at the other extreme come the engineers. So always the world is divided between philosophers and engineers, right? And the engineers don't care if it's true or not, but they care if it can be applied. So, if it's true that quantum mechanics generates randomness, is it possible that quantum devices are better at generating randomness for cryptography than other ways of generating randomness through noise or through thermal fluctuations or other stuff? Okay. I'll try to answer the first question first. The last one we leave it for the. I'm a philosopher more than an engineer. So, how do we certify intrinsic randomness? Okay, I have 10 minutes to explain you this. So, this is a random number generator for a theorist. If you want a real one, you can go to our labs. Not my lab, because I don't have any, but the labs of my colleagues, and you will find some random number generator there. So it's a box that splits a list of zeros and ones, and then, well, if you look at that list, you don't find too much of a structure, so you would say, well, what is the next bit that is coming out of that? How to predict, right? So then it's a random number generator, because it's how to predict what is the next bit that is coming out of that thing. Now, how to check that this thing is random? Because, for us, maybe for us humans is already a lot, but for a computer to check maybe this list exactly the same as there, repeats itself. Okay, so the next bits that come out are exactly the same, and exactly the same. For a computer, it's very easy to check that these 20 or whatever written there bits are repeating themselves. So how do I check that such a thing is random? Seriously. Well, people normally run statistical tests. Like, let's check the 0 and 1 appear more or less half of the time. Let's check the 0, 0, 0, 1, 1, 0, and 1, 1 appear more or less 1/4 of the time, and so on. Correlations and other stuff. So you can run these tests, and indeed you can. There is an official battery of tests by NIST, National Institute of Standard Technology in the US, that you can run, and you certify according to NIST criteria that your random number generator is random. And you send them the list, they run the thing, and they tell you yes or no, you pass these tests, or the other ones. Now, even if you pass the test, there is a problem for cryptography. So imagine that I have a real random number generator, I produce that list, so it really passes all the tests, it's fantastic. I burn a DVD with that list, and I pass it to you claiming this is a random number generator. Obviously, your random number generator will pass all the tests as well. But I have a copy. And so you use this for security, for your passwords and so on, and I have all your passwords. Right? So that's a bit of a problem with this kind of test, statistical test. It can test the product, but it cannot test the device. It's called product randomness and not process randomness. It doesn't test that the process is random, it tests that what comes out is how would have been how to predict. And the quantum randomness, I'm going to prove to you that with quantum physics we can certify that the process is random. So we can certify that what's going on in that box is really creating information. And this is the theorem of John Bell. Now I need to change a little bit the scheme. First of all, I need 2 boxes instead of 1. Price to pay. And there's always some price to pay in order to get some interesting stuff. and I need also a button on these boxes. So it's not just the box spitting numbers, but if I want a number, I have to push a button. And I have the choice between two buttons, or 3 or 4, but I will take 2. And these are our main characters, Alice and Bob, that always appear in discussions of cryptography. So imagine that there are these two boxes. I give one to you, I keep the other one, and then we want to generate a number. I push my button, I get a number, I push a button, I get a number, and keep going. And this comes out with a list of numbers. Okay, that's the scenario in which we are. Now we want to prove that what is coming out of these boxes is not pre-recorded. Okay? I want to exclude the possibility that these boxes are actually reading from a DVD that someone else put in there, and this person knows all the information. By the way, I want to stress at this very point that nothing that I'm going to do now is quantum. Okay? So there's nothing here that you cannot understand. This is something you could, or you can compute for that matter. This is purely classical. This is what I would do to cheat you. So, or you do to cheat me, so it's fine. So this is the assumption we want to exclude. That when I push the first button, there is something in the box that says, okay, if this button is pushed, you output 0. And if the other button is pushed, you output 0 or 1, depending. It's already written inside. We are reading a piece of information that is already pre-written in the box. Of course, you can now phrase it in quantum physics. I'm measuring in physics. No, I'm measuring a degree of freedom in physics, and I would like to know if the result of the measurement is pre-existing. Okay, now for mathematical simplicity, in order not to bother you too much, I will change notation bits from 0, 1 to +1 and -1. I hope you agree that nothing is lost in this transformation. And now come my mathematics. And sorry, this one is going to be tough. Okay, so these are my bits, +1 and -1, so it's pre-recorded there. The first piece of mathematics is this. This product is either +2 or -2. That's super cheap, right? Well, let's look at it a little bit more carefully, right? We have a proof here. Yeah, so suppose that, for instance, B0 is equal to B1, then this term is 0. And this is what is B0 times B0 plus B1, so 2B0 times A0. Okay, now A0 and B0 are plus and -1, so this is plus or -2. If they are different, it means they are opposite, but this is 0, and this is plus or -2. So the first piece of mathematics essentially uses 1 + 1 = 2 and 1 - 1 = 0 to prove Bell's theorem. So we are in one of the deepest results of science in the last century. Now, this is probably the most difficult step. The sum of the averages is the average of the sum. So what happens? Remember that each time I can push only one button. Okay? So clearly I cannot measure this number. Because if I push the button 0 and this one push the button 1, I got a A0 and a B1. I didn't get the B0 and I didn't get the A1. So I cannot compute this number here. What can I do? Well, I can capitalize on the fact that the average of a sum is the sum of the averages. Right? To compute your cap after 2 semesters, you can either compute the cap in each semester and do the average of those, or compute the cap per class and average those. Right? These things commute. So, so now I can take the average of S, will be the average of the times when I measured A0, B0, the average of time when I measure A0, B1, the average of this, and the minus the average of that. There's this minus sign there that appeared miraculously, let's save the day. Right? Okay, so we have something, and now the flash of the obvious. The average must be smaller than 2. Right? Because if I'm taking an average of a number that is supposed to be either +2 or -2, I will not get 3. Right? Your cap will never go above 5. Don't even try. Why? So this is the, in fact I should now change this presentation and put this thing at 5. I could do it. And then I can, so this is essentially the statement that if your grades go between 1 and 5, well, your cap will be 1 and 5. Okay, so here, so if these numbers exist, this S is plus or minus 2, so the average is between -2 and 2. And this is the famous theorem by John Bell. That's it. Okay, I think if you are not sleepy, you can go home in the bus and you can write it on a piece of paper, you can really write it. Okay, that's Bell's theorem. if one observes, now, what is the opposite of this theorem? So, suppose somehow that one observes S larger than 2. What does it mean? Well, it means that this guy do not pre-exist. Right? If A implies B, non-B implies non-A. So, irrespective of the fact that this actually happens in nature, this is already a very interesting intellectual achievement. So, I don't think any of you, or myself for that matter, before learning all these things, would have been able to come up with a criterion to prove that something is not prerequisite. It's not that easy. Right? Well, here it is. And it's not that difficult to prove either. So, what is the relation between this and randomness? Well, look, if assume that these numbers are not pre-existing, so I can prove that it's impossible they are pre-existing, then nobody can predict them. Why? Because if someone could have predicted them, he could have written them in the boxes. Right? So, the fact that it's non-pre-existing implies that nobody could have predicted those lists. So it's random. So this means that if I have a violation of this inequality, I have something unpredictable for all normal, irrespective of the computational power. That's what it means. Even with a super powerful computer, it's impossible to predict. It just doesn't exist. Okay? So far it was about logic. So if this happens, then something. Can it happen? And I want to cite again a historical anecdote that Boole, when he derived Boolean algebra, binary algebra and these kind of things, he derived Bell inequalities actually. So people after Bell, many years later, they browsing Boole's book, I didn't check the date, found that some Bell inequalities are written there. But of course the guy said, well, these are obvious, these must be obviously satisfied. So somehow he couldn't imagine that this could be possibly wrong in nature. But it is wrong in nature. And the experiment looks like this. Okay, from now on, this is one slide you have to trust me. So far, I presume that you should be able to reconstruct all that I said. Now you have to trust me because this one I'm not going to be able to explain. So this is how the source that produces these random things looks like. In fact, well, what is there here? There is a laser. It's a photo taken in the lab of Christian Gurziffer here. There is a laser here producing blue light. In the middle here, there is a small crystal that looks transparent. Here is represented by the fact that most of blue light goes through. But from time to time, the vibration on this crystal, so these photons excite the vibration of the crystal. Typically what happens with the panes, right? The light excites the vibration, these electrons move, and the light comes out. In this kind of crystals, for some strange reasons of the crystal, from time to time, these vibrations, instead of just propagating the light out, generate two vibrations at half the frequency. Energy is conserved, the total frequency here is split in two, but this generates the two photons, the two particles of light, that are so-called entangled. And okay, this is something that is the name that we've given to it, and it has a clear definition in quantum theory, but I don't have time to explain to you what it means. Now we take these photons and we send them through optical fibers, normal optical fibers, through some measuring stations. What these measuring stations do? They measure polarization, for instance. You know, polarization of light is the plane in which the electric field is oscillating. So there is vertical polarization, horizontal polarization, 45-degree polarization, minus 45-degree polarization. And you may know or not know, I hope you know from high school, that polarization can only be measured. So if I send you a beam of light, in principle you can only measure either if the polarization is horizontal or vertical. Or like this. That's sort of a basis measurement. Although if your brain is still on, you realize that what I said is wrong. But for a single photon is correct. And if you do this experiment, you find S larger than 2. In fact, in the lab of Christian, they managed to achieve almost the highest possible value is 2.8284, 2 times square root of 2. So a few dates just to finish. I told you that Bell theorem is 1964. And I hope you are able to rederive it now, going home. The first test, so that's also another thing. Okay, John Bell, people say, why do you care about this philosophical business? They are just there are more things to compute. In 1964, there's these things to compute in high energy physics. Nowadays, not so much. Oh yeah, there are, but I mean, You need to be super, super strong. And so some people still are a bit interested. They started studying these. Okay, let's try to do some experiments. And they found out that with all the body of knowledge accumulated in quantum experiments, there were no data that could be checked to match the experiments of Bell. So someone had to come up with a new experiment. And they find in 1970s, try to do something. They're not very conclusive. So the first clear evidence that quantum mechanics is correct, the prediction of quantum theory is correct, and that the results are not pre-existing in 1982. So I can safely say that before 1982, or before 1964, depending how you look at it, it was very possible to believe that there is no randomness in nature, and that this interpretation of randomness is just an interpretation that some people like for philosophical reasons. Okay, since then there have been plenty of experiments, so there is absolutely no doubt that this phenomenon is real. So it's not an accident. It's been repeated many times for many reasons. Also here, by the way, not only with 2 photons, with 2 ions, 2 atoms, more photons, all kinds. And last year there were what they call loophole-free tests. If you are really super paranoid, there were objections that you could make to the previous experiment, and finally in 2015, last year 3 groups closed the objections, all of them at the same time. The different objections have been closed in the different experiments, but none of them together. Not all of them together, and finally it's done. So somehow there's really no reason to, and there are some applications on which I'm involved. Okay, final balance. So is there randomness in nature? Well, I would say the statement, as usual, we are not in a Donald Trump campaign, so the answer is not yes or no, no? Or whatever. So the statements in science are a little bit elaborated, right? The correct statement is this: that the evaluation of binary equality proves that there is a generation of numbers that were not pre-existing. And as I prove to you, this statement does not rely on quantum theory. So someone cannot come and tell me, oh, but maybe quantum theory is not an exact description. One day we will have a better theory. No. The proof that I did is purely define what it means pre-existing and come through it. It doesn't rely on the theory that I'm using to overcome this problem. Now, you may know, or if you don't know, you learn that there are some deterministic interpretation of quantum physics, nevertheless, because determinism is hard to abandon. It's possible, but you have to postulate some physical realities that we cannot have access to. There is one called Bohmian mechanics, in which essentially it comes down to saying that there are physical influences faster than light that you will never be able to exploit. So don't start thinking of traveling faster than light, but nature does it. So it looks like a conspiracy theory, like nature does it, but you can't. And then there is the famous multiple universes, many worlds, or whatever. That is a different way of, so then the price to pay there is that fine. I'm not sure that this is conclusive, but there are a lot of discussions there. But anyway, the price to pay is that there's not only one universe, but many of them. And I need to invoke the fact that there are many of them in order to explain what I see in my universe. Fair enough. The point is, I'm fine with all of them. Just you know what price you have to pay. Right? And pay the price. I mean, be consistent. Of course, if you go very far, please remember that full determinism cannot be falsified by observation. So if you have a conspiracy theory in which, for instance, every single thing that happens in this universe has been written down at the moment of the Big Bang, everything, including what I'm saying now, including what you're thinking now, well, then at the moment of the Big Bang, someone had written down that when someone goes to the lab and does one of these experiments with entangled photons, they would violate the Bell inequality. This is a non-local cause in the past. It's something like, everything is determined in the past, then everything is determined in the past. Right? If you try to convince me that it's not the case, then I can tell you, well, you are pre-programmed to try to convince me. If you are in one of these kind of super deterministic interpretations that nowadays, I have to say, for those, physics has gone through super determinism. Now we are already out of that. Now is the time of the biologists. Right? The neurosciences and so on. Now, what in the brain is already predetermined and so on. Now they will come out as well. Just 1 century later. It's the development. Science normally starts with determinism, is good. Now neurosciences are sort of deterministic basis, at least we can do something, but I'm sure that's not the end of the answer. Now, some of you can answer, even ask sort of religious questions like random for God or for whatever preference you have. And I mean, at least for the kind of notions of God that I'm familiar with, God is outside time. so there's nothing to predict, right? If you're outside time, well, you're outside. So all in all, the answer is, I would say, for us in this universe, so not for God, not for multiple universes, not for us, in this universe there is randomness. And I think this is, I would find hardly any colleague would dispute this. Unless, of course, you go to full determinism. You will say no. And there are some people who. Okay, last slide is quantum randomness useful. Well, there are some quantum random number generators already being sold. You can buy one. I'm not sure if it's a good idea. You know, in many cases, my point is that in many cases the decision can be practical. So, if a quantum random number generator is cheaper, faster, or more stable than the one based on a temperature fluctuation over a resistor, then buy that one. Okay? And remember that quantum doesn't mean complicated, big. Right? One of my colleagues, Alex Lin, you can invite him for the next talk or another talk, is sending quantum experiment into CubeSats. CubeSats are satellites of that size, and they put a whole quantum lab, like the one I showed before, in that thing, send it up, survives the launch, and still creates entanglement, violates Bell inequalities out there in space. So, quantum doesn't mean nowadays big things, accelerators, and whatever. So you could have one day a quantum random generator in your handphone if the market wants it. Okay, so don't associate quantum with the CERN or LIGO, although these are also quantum. And well, of course, this Bell inequality business gives a small advantage. And this is like advertising from my research, is that the randomness. If I have a random number generator based on Bell inequalities, I can certify it without knowing what it's actually doing. Okay, because I didn't tell you. When I did my proof, I didn't tell you that I was using photons, atoms, and so on. Just give me some boxes, I play with it, violate Bell inequality, it's random. No need to know what physics is going on. Okay? This is famous cartoon by Dilbert. I finished with this. So Dilbert is the engineer that goes to the accounting department. You see that the guy has a very respectful idea of what an accountant is. And then they find the random number generator of the department, which is that thing. And then Dilbert asks, well, are you sure that's random, no? And then very smartly, the accountant says, that's wrong with randomness, you can never be sure. Indeed, if you toss a coin, and you see head, it may be a perfectly well-balanced coin, because that sequence has the same probability as any other sequence. Right? However, if you toss a coin and you see more than 10 times head, you may start believing that there's something great there, no? And anyway, with quantum mechanics, you can. That's what I tried to prove you. And okay, we're working on that, and we'll finish. Thank you very much.
Now, we have a short Q&A session. Does anyone have any questions for Professor Scarani? So if there's no questions, thank you Professor Scarani for talking. Physics Society actually presented a gift for you. It's not a custom, but it's a classical mark.
Oh, it's very useful.
Yeah.
Beauty will pick up
okay.
Thank you very much.
Thank you. So, one more. Please help yourself to refreshments, and we hope that you guys will come to the next one again. We're actually planning so we had so I would hope that we can see most of you there again. Thank you.
Guys, if you all want to interact with the speakers, you feel free to just